everyone. I'm going to go over some basic biomechanical factors and concepts that you need to know that are really going to be essential when you take biomechanics as a course later on. So, when we talk about the body, it's easier to think about it like a machine. So machines function in four ways. They balance multiple forces, right, the internal and the external. They enhance force in an attempt to reduce total force needed to overcome a resistance. They enhance range of motion and speed of movement so that resistance can be moved further and faster than the applied force. And they can alter resulting direction of the applied force. And I'm going to explain what all of these mean through this PowerPoint today. Okay. So the musculoskeletal system arrangement provides for three types of machines in producing movements: levers, which are the most common, wheel axles, and pulleys. And so humans move through a system of levers. Kind of think about it like instead of having muscles, they would be ropes that get pulled, for example. Levers cannot be changed, right? You can't change the configuration of where your joint is, which is an axis, or the length of the lever, etc., but they can be utilized more efficiently. So a lever is a rigid bar that turns about an axis of rotation or a fulcrum. The axis is the point of rotation about which a lever moves. Okay. So if we think about a lever here, I'll show you an example. This is what we're talking about. Here's our lever. It's this piece of wood, okay? In the human body, the bone represents the bar. Okay? And you can't change the length of the bar, correct? Your bone can't get any longer just because you wish it to. The joints are the axes, okay? And that's where, of course, the rotation is going to occur. And the force is our muscles, right? It's the contracting part which causes the lever to rotate around the axis. And we can actually apply resistance. That resistance could be the weight of an arm, for example, could be a dumbbell, it could be a box or anything like this. So we can actually change the resistance that is applied. So this is a good overview slide about the levers that I'll talk about today. There are three types, and they're configured in different ways. The first order here, what you can see is that you have the lever on one side, the fulcrum in the middle, and the effort or the load on the other. So for example, this is a claw hammer where the force is applied in the middle of the lever and the effort. Another example is pliers, okay? And you can see this in the human body here, where you've got your effort here in your scalenes, your fulcrum is in the middle, and then your resistance is via the head. You have a second order where the lever is in between the fulcrum and the effort, the force and the effort, okay? Example is a wheelbarrow or a nutcracker. And we can see this type of lever in the human body, in the gastrocnemius here, where that effort, that forces the resistance in the foot, and the fulcrum is right on the metatarsals. And the third order, which is most common, is when your effort, the force that you're going to apply, is in between the fulcrum and the lever. For example, in the biceps brachii contracting to lift a weight. Also in a pair of sugar tongs. So you apply, here's your fulcrum, your effort gets applied here to the lever. And I'm going to go through each one of these in turn today. So 3 points determine the type of lever and for which kind of motion it is best suited. You've got your axis here, otherwise known as a fulcrum, again is the point of rotation. If force is the force application, usually in the case of the musculoskeletal system is the muscle. And point R, resistance, And this could be a location of external resistance or the center of gravity of a lever. So those are three very important parts that you'll need to remember, okay, and understand. Again, we have a first class lever where the axis is in between the force and the resistance. So this axis is also called F for fulcrum, okay. The second class is when the resistance is between the axis and the force. And the third class is when the force, the effort, right, is in between the axis, the fulcrum, and the resistance, the load. So you can see here that there are two different types of terms. Sometimes they will call an axis an F, which is a fulcrum. Sometimes the force, for example here, is known as E, effort. Okay, and R, resistance, is sometimes called the load or the lever. Okay, so don't get those mixed up. They're just kind of interchangeable terms. So first class levers produced balance movements when the axis is midway between the force and the resistance. Okay, for example, a seesaw. You can see the axis is exactly midway between the force and resistance. It can produce speed and range of motion when the axis is close to force. So you see this, the triceps and shoulder extension, and elbow extension, really close to it, provides a lot of range of motion as well as speed. And it can also produce force motion when the axis is close to the resistance, right? So you require a lot of force in order to actually overcome that resistance. Some examples of first-class levers that you might see is the head that's balanced on the neck in flexion and extension. So the agonist and antagonistic muscle groups are contracting simultaneously on each side of the joint axis. And the agonist produces force, while the antagonist supplies resistance. So here's our axis of rotation and flexion and extension, right? So in this case, if I'm going to flex, here we go. The force here is applied by this scalene muscle, for example, and the resistance is by the weight of the human skull. So when force is applied, it's where the muscle inserts into the bone, not in the belly of the muscle, okay? So in this case here, when we're talking about force, this is an elbow extension where the shoulder is fully flexed and the arm behind the ear. The triceps applies force to the olecranon of the ulna right here, behind the axis of the elbow joint. So not in the belly, down here where it actually attaches onto the bone. As the applied force exceeds the amount of elbow resistance, the elbow will actually extend. So by applying force here, what's going to happen? This is going to swing outwards, right? And actually extend the elbow. Second class levers produce force movements since a relatively large resistance can be moved by a relatively small force. So think about a wheelbarrow, a nutcracker, loosening a lug nut on a car, for example, or raising the body up on the toes. So on the second class levers, to remind yourselves that resistance is in between the axis or the fulcrum and the force or the effort. So look at this wheelbarrow, the resistance is right in between, and the axis, by applying force, upwards force, you can actually overcome the resistance to move the wheelbarrow. In the case of the nutcracker, heavy resistance in the middle close to the axis here, and by applying inward force, we can actually crack this resistance. So there are relatively few second-class levers in the body. One example, though, is plantar flexion of the foot to raise the body up on the toes. So here we go. We've got our joint that looks like this, our system. Our axis of rotation, our fulcrum, is going to be right here, up on the up on the tibio-articulate, right onto the tarsals. There we go, Okay. The ball of the foot is the axis. And then the force is applied here on the calcaneus because of the gastrocnemius muscle, okay, and to overcome the resistance of the body at the tibial articulation here. And by applying this upwards force, putting pressure on this axis of rotation, we can overcome the resistance. And then what's going to happen? Our force here, the calcaneus actually lifts upwards. Third-class livers are most common in the human body. They're there to produce speed and range of motion movements, and they require a great deal of force to even move a small resistance. Some examples here is paddling a boat and shoveling some dirt out of a ditch. So looking at our third class, we have the force, which is in between the resistance and the axis here, our fulcrum. So in the sailboating, for anybody that's done that, look, he's trying to get away from a shark. The axis of rotation is the hand, and by applying force through the muscular system, we can actually overcome the resistance on the water and move the paddle backwards, right? And therefore propel the boat forwards. For shoveling, again, using the hand as the axis of rotation, the resistance is how much dirt we have on the shovel, okay? And the fulcrum is, the force is on the other hand, which we use to shovel the dirt out. In the body, one of the best examples is the biceps brachii in elbow flexion. So again, force is in the middle of resistance and the axis. Here in our body system, we have that axis of rotation here is at the elbow joint. The biceps brachii applies force at the insertion of the radial tuberosity, so down here, okay, to rotate the forearm up to overcome any resistance application. That could be, for example, just the hand, could be a textbook, it could be a weight. And when you apply enough force, the joint will actually move around the axis of rotation to produce elbow flexion. Okay, so those are the three levers that are in the human body, keeping in mind that most of the levers that we see are of the third class type. So, torque, which you would have read about in chapter 3, and I hope made sense to you, is the moment of force or the turning effect of an eccentric force around an axis. And when we talk about an eccentric force, it's the force applied in a direction that is not in line with the center of rotation of an object with a fixed axis. So, in objects without a fixed axis, though, it's the applied force that is not in line with the object's center of gravity. So for rotation to occur around a joint, an eccentric force must be applied. So often we purposely increase our force arm length in order to increase torque so that we can more easily move a relatively large resistance. Said another way, we can increase our leverage. So looking at this equation here, force times the force arm, which is basically the same as saying the mass arm, is equal to resistance times the resistance arm. Okay. And the resistance arm here is the distance between the axes, for example, of that elbow joint, and the point of resistance application. And in our third class example, it would have been holding a weight in the hand. So because we know the resistance arm, the distance, right, and we know, if we know how much resistance there is, maybe a 10-pound weight, we therefore can know how much force we have to apply in order to overcome the distance from between the axis and the point of resistance application and the resistance weight. So there's an inverse relationship between the length of the two lever arms, between the force and the force arm, between resistance and the resistance arm. So the longer the force arm, that FA, the less force is required to move the lever if resistance and the resistance arm remain constant. Shortening the resistance arm allows a greater resistance to be moved if force and force arm remain constant. So you just have to think about to understand that, think about this equation, okay? Force times mass arm. is equal to resistance times resistance arm. Again, so therefore, for example, if you know that you can get a longer force arm, if the resistance and the resistance arm remain constant, they don't change their value, and why would they? You would need less force to move the lever. So thinking about that biceps brachii example, lifting a weight, the resistance wouldn't change. You're still holding a 20-pound weight. And the resistance arm, that's the distance, right, between the axis and the resistance point. That's going to remain constant. So if you can increase the force arm, or you can make the force arm longer, you require less force to move it, for example. So there's a proportional relationship between force components and the resistance components because they're equal to each other. If either of the resistance components increase, there must be an increase in one or both of the force components. Okay, that just follows logically from the equation. Even slight variations in the location of the force and resistance are important in determining the effective force of the muscle. Okay. So therefore, you need to make sure you have an accurate calculation of your resistance, of your force, and as well as, for example, of your resistance arm. So, an example, if force arm here, right, which is the distance from the force to the axis, and the resistance arm are equal in length, you would need a force equal to resistance to balance it. Therefore, you would need more force than your resistance in order to actually cause this to tilt on its lever. Okay? If the force arm is longer than the resistance arm, you only need a small amount of force in order to move a relatively larger resistance. And as the force arm becomes relatively shorter compared to the resistance arm, you're going to need a lot of force in order to move just a little bit of resistance. So B is really optimal, right? If you can increase that force arm, you don't need as much force to move a bigger resistance. The human body, the leverage that we apply is built for speed and range of movement at the expense of force. And we're mainly built of third-class levers. So we have short force arms and long resistance arms. They both require great muscular strength in order to produce movement. Human leverage for sports skills requires several levers. For example, throwing a ball involves the levers at the shoulder joint, at the elbow, and the wrist joints. The longer the lever, the more effective it is in imparting velocity. So, for example, Serena Williams, an amazing tennis player, can hit the tennis ball harder with a straight arm drive than with a bent elbow because the lever becomes much longer, right? And therefore moves at a faster speed. So that's levers. I hope it's fairly simple. You may have to go through it and use some examples. But now let's move on to laws of motion and physical activities. So body motion is produced or started by some action of the muscular system, right? And motion cannot occur without a force. So the muscular system is a source of force in humans, right? That's how we generate force, via our muscles. And when we generate that force via our muscles, we actually produce movement. Things happen, right? Our arm moves, our leg moves, our head moves. And Newton's laws of motion have many applications in everyday life, but also to movement of the body. We're talking about inertia, acceleration, and reaction. So here's our law of inertia. The way it's stated, I'll read it for you. A body in motion tends to remain in motion at the same speed in a straight line unless acted on by a force. The same way that a body at rest tends to remain at rest unless acted on by a force. So let's say this car is static it's going to remain static, not moving, right? There's no acceleration. Let's say it's parked. It's going to stay that way until you get another force that acts upon it. In this case, that force is this orange car that is acting upon it. Boom, and it's crashing into it. Okay. And once that happens, then the body is going to move from its stopped position to actually move forward. That's just how it works, right? So muscles produce force to start, to stop, to accelerate, to decelerate, and change the direction of motion. That's how we're moving our inertia. Either we're not moving at all, or we're moving at a constant speed, right? Constant velocity. And we use our muscles to change that. So we can do that internally via our own muscles, or we can do it when somebody pushes into us, for example. So inertia is resistance to action or change. I think most of us are pretty much like this. We like inertia. We like to be where we are. In human movement, inertia refers to resistance to acceleration or deceleration. So both of those, okay? And it's the tendency for the current state of motion to be maintained regardless of whether the body segment is moving at a particular velocity or is motionless. Okay. So some people think that it's only when you're motionless, but no. It's both when you're motionless, when you're not moving, or if you're moving at a particular velocity, a particular constant velocity. So the reluctance to change our status requires force in order to change that. And our force, again, is produced by our musculoskeletal system. The greater the mass of an object, the greater its inertia. It's easy to move a small object sitting on a desk than a large one, correct? It's easy to move a box that's sitting on a table than move an apartment complex. Those things have a greater mass and therefore greater inertia. So to overcome this inertia, you need to apply force. So the greater the mass, the more force is needed to significantly change the object's inertia. If you're trying to move a 100-pound person, you don't require as much force as if you were trying to move a 250-pound person, right? You have to apply more force to that heavier individual because they have more mass. Here's some examples of inertia. So force is required to change inertia. Any activity carried out at a steady space in a constant direction will conserve energy. That's why we like it, right? Running, you just run at a steady pace, and you use less energy. Any irregularly paced or directed activity will be very costly to energy reserves. So here we see a Bayern Munich player, and he is switching directions. And here our defender, I think that is from Barcelona. In order to actually change directions that way, it requires the force of the muscles. When you then use those muscles, they require oxygen, right? More energy. Same with when you're weightlifting, for example, that big sudden pull to change our position requires a lot of energy, a lot of oxygen. And that's why we get more fatigue playing handball, if anyone knows what that is. It's a great game. And basketball than when you're jogging. Handball and basketball are much more fatiguing because you're constantly changing directions. Here's a great example of inertia. This motorcyclist has crashed off the off the track into the tire barrier. These barriers here have actually applied a force to stop the motorcycle. But not the motorcyclist. And here is inertia, and he's going forward, right? He didn't want to stop that forward motion. So the second law is the law of acceleration, and it's defined as a change in the direction of a body that occurs in the same direction as the force that caused it. So the change in acceleration is directly proportional to the force causing it, and it's inversely proportional to the mass of the body. And of course, we know that acceleration is rate of velocity. So, acceleration is equal to force divided by mass. Okay, just one moment, I have to pause. Okay, sorry about that. So here we go. Acceleration is equal to force divided by mass. In our example here of our husky pulling a maybe Santa's goodies, we can see that the mass of this bag is 500 kilos. That's about 120 pounds, okay? And the force is 100 newtons in order to move this mass, okay? And by knowing these two, force divided by mass, you can calculate the acceleration. So 100 newtons divided by 50 kilos will tell you how much acceleration that you need to actually exert to move this. So a much greater force is required from the muscles to accelerate a 230-pound man than to accelerate a 130-pound man running at the same speed, because the mass is larger, right? So looking at our example here, the bag is remaining constant at 50 kilos, okay? So if you can apply twice as much force, you're in a much better state to actually move it than one person. You're going to accelerate much faster, right? Think about having a more powerful engine in your car to move the weight of the car. You accelerate much faster. You get from 0 to 60 much faster. That might be a good way to think about it. So the last law is the law of reaction, which states, for every action, there is an opposite and equal reaction. Now, sometimes not in human life, right, in our behaviors, but the laws of physics state that. So as we place force on a surface by walking over it, the surface produces an equal resistance back in the opposite direction to the soles of our feet. We don't feel it, but it's there. So when our feet push down and back, the surface actually pushes up and forward. And the force of the surface that's reacting to the force we place on it is known as the ground reaction force. And you're going to hear about that a lot in biomechanics. So we provide the action force, while the surface provides the ground reaction force. And it's easier to run on a hard track than on a sandy beach because of the difference in the ground reaction forces of the two surfaces. A solid surface, a firm surface, provides more ground reaction force, equal and opposite, than a sandy beach does, right? The track resists your propulsive force, and the reaction from the ground drives you forward as you're running. So those are Newton's three terms. Another term that we should get familiar with is friction. So friction is a force that results from the resistance between between the surfaces of two objects from moving upon one another. And depending on the circumstance, we might want increased friction or we might want decreased friction. So, for example, it's not always the case that less friction is better. So to run, we depend upon friction forces between our feet and the ground so that we can exert force against the ground and propel ourselves to go forward. If, for example, we had reduced friction, like if the ground was slick, or we had slippery shoes on, or we had socks on, well, the surface friction would be reduced and we're more likely to slip, and therefore you can't move forward. Conversely, in skating, like ice skating, we desire decreased friction so that we can slide across the ice with less resistance. There's two types of friction, static friction and kinetic friction. Static friction is the amount of friction between two objects that have not yet begun to move, right? Henceforth the term static. Friction occurring between two objects that are sliding upon one another are called kinetic friction. Now, static friction is always greater than kinetic friction. And you can try this, and you know this by actually doing an experiment. So it is always more difficult to initiate dragging an object across a surface than to continue dragging it. Okay? You move, so kinetic friction, when you're moving, less force is required than static friction. Static friction may be increased by increasing the normal or perpendicular forces pressing the two objects together, such as adding more weight to one object sitting on the other object. Okay. For example, having a 4-inch by 4-inch block on a table, if you increase that to 10-inch block, you're going to increase the static friction between the blocks and the table surface. So we can actually calculate coefficients of friction, and this is the amount of friction forces. And the way you do this is you consider both forces pressing the two objects together, and this coefficient of friction depends upon the hardness or the roughness of surface textures. And the coefficient of friction is the ratio between the force needed to overcome the friction over the force holding the surfaces together. So we have a higher coefficient of friction when they are closer together than if they were far apart. You have a lower coefficient of friction. You have a lower coefficient of friction socks on a linoleum floor than if you're wearing hiking boots, for example. So force. Muscles are the main source of force that produce or change movement of a body segment, the entire body, or some object thrown that's struck or stopped. So if I ask you a question about what produces force in the body, you should know that the answer should be muscles. Strong muscles are able to produce more force than weak muscles, okay? Both in terms of their maximal force that they can produce as well as sustained exertion over a period of time. Strong muscles get less fatigued than weak muscles. And these forces either push or pull on an object in an attempt to affect motion or shape. Without forces acting on an object, there would be no motion. Things would not move, our body would not move without the muscular forces that act upon a joint axis, for example. So force is equal to mass times acceleration, written in long form here, and also in short form, which is also why when we rearranged that and looked at acceleration, we know that acceleration is equal to force over mass. So the weight of a body segment or the entire body times the speed of acceleration determines the force. This is important for sports such as football, judo, and wrestling. So if I need to know how much force to apply on an individual to take them down in wrestling, my head kind of does a calculation about how much mass is there of my body to accelerate and how fast I have to accelerate, right? This is important in activities using only a part of the body, such as lifting a pen, right? You require force to do that. And in throwing a ball, for example, the force applied to the ball is equal to the weight of the arm times the speed of acceleration of the arm. And of course, leverage factors are important. How long our arm is, right? When we have a longer lever, we don't need to produce as much force to move an object. So, many activities, particularly the upper extremity, the upper body, your arms, require a summation of forces from the beginning of the movement in the lower segment of the body to the twisting of the trunk and the movement at the shoulder, the elbow, and the wrist joints. So that force has to come from all over the body. Think about a golf drive. That requires force over the whole body. Shot putting, discus, and javelin throwing, right? We don't just consider the force at the joint. We have to consider all of the forces summed together from all over the body. We can use momentum, right, which is equal to mass times velocity, m times v, to help us with force. When we have momentum, it doesn't require as much force. Think about when we are on a bicycle. When we're static and we have to push off from the traffic light, right, it turns green, we require a lot of force produced into the foot in order to propel us forward. But once we're biking, we don't use as much force, right? We're using the momentum. And the greater the momentum, the greater the resistance to change in the inertia or state of motion. Also want to talk about balance, equilibrium, and stability. Balance defined is the ability to control equilibrium that is either static or dynamic. Equilibrium is defined as the state of zero acceleration where there is no change in the speed or direction of the body, right? We're at a state of equilibrium. Think about it, we're in a state of Zen. There's no change, our mind is clear, kind of like that. We have static equilibrium where the body is at rest or completely motionless, or we can have dynamic equilibrium where all applied and external forces acting on the moving body are in balance, resulting in movement with unchanging speed or direction. So we're moving, but it's constant. To control equilibrium and achieve balance, stability needs to be maximized. And stability is the resistance to a change in the body's acceleration, a disturbance of the body's equilibrium. And stability is enhanced by determining the body's center of gravity and by appropriately changing it. And center of gravity is the point at which all of the body's mass and weight are equally balanced or equally distributed in all directions. So, and of course, balance is important both when we're at rest, when we're not moving, as well as when we are moving. So look at this here. This is our general body. Let's just imagine this as a person. In this configuration, you can actually calculate that the center of gravity is much lower because this person is it's bottom heavy, right? If you were a rectangle, boop, 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 your center of gravity would be higher. So here we are in our base of support, and our center of gravity is allowing us to remain balanced. But when we have a pull of gravity and we've got torque, right? See how we move around that center of mass? And a person has balance when their center of gravity falls within the base of support. So see how we're not moving outwards. When you go outside of that base of support, you're going to fall off. You're going to fall forward or something like that. So a person has balance in the direct proportion to the size of the base. So when your legs are together like this, see your center of gravity? It's higher. You are more likely to fall in this configuration than if your base of support is a lot wider because your center of gravity comes much lower. It's very similar to a car. A car that is skinny, right, has a higher center of gravity. It's unstable going around a corner compared to a car which has a wider base of support, lower center of gravity, more stable. So the larger the base of support, the more balanced you are, or any object, in fact, is. Third, a person has balance depending upon the weight or the mass. So the greater the weight, the more balance you have. Okay. This car also is a lot heavier than this one would be. Fourth, a person has balance depending on the height of the center of gravity, as I just said. So if we have a car here, this is that skinny car, small base of support, wide base of support, lower center of gravity. As you're going around a corner, the car with the smaller base of support and higher center of gravity is going to lose its base, right? It's going to be unbalanced compared to one that has a wide base of support and a low center of gravity. The lower the center of gravity, the more balanced you are. 5, a person has balance depending on where the center of gravity is in relation to its base of support. The lower the center of gravity, the more balanced you are. So the balance is less if the center of gravity is near the edge of the base. Going down, keeping it close. So here's our sumo wrestlers. In anticipation of an oncoming force, the sumo wrestler is expecting him to attack forward. Stability can be increased by enlarging the base of support. See, both sumo wrestlers have wide legs in the direction of the anticipated force. Notice that they're not standing with their feet flat, right, in a line. They're actually distributing it. One is further back, see that one there, compared to this one, because he's expecting, our black sumo wrestler is expecting his opponent to go forward at him, so he needs to have 1 foot back. And the last point is that equilibrium may be enhanced by increasing the friction of the body and the surface it contacts. Okay, and this is why they apply that chalk. They use the chalk, then they use the sand, make sure their hands are dry. And of course, rotation about an axis aids our balance. Therefore, a moving bike is easier to balance than a stationary one. Okay, in order to maintain our balance, our equilibrium, and our stability, we use some people call the kinesthetic physiological functions. I just call them the input sensors. These, of course, are proprioceptive of the muscle, the joint, and the skin, which you learned about in your neurological considerations lectures. We use visual input from the eye, vestibular input that is in the ear. We use our central nervous system where all of these things are coordinated and integrated to control our eye movements, to control the postural control of the muscle, and that allows us to have balance. And of course, when we have a dysfunction in one or many of these systems, we become imbalanced or we become dizzy. All right, that's why if I make you close your eyes and spin around 10 times, you open your eyes, you try to balance, what happens? You get dizzy. Because I take away vision, and I muck around with your vestibular system's ability to know where it is in space. Okay. That's the end of the slideshow. I hope that makes sense. Please let me know if anything's not clear, and I will clarify it either online or in person. Thank you.